I'll present work that I've done with Katrina Falkner. And I would especially like to thank the two first presenters that have set up the scene for my attack. And now that you all think that everything is safe, we'll change all of that. So memory has always been short. We always have been short on memory. My first computer was an Apple IIe. I had 64 kilobytes of memory. That wasn't enough. Currently, I have 5 orders of magnitude more memory, and as you can guess, it's still not enough. And what have happened is that operating systems now offer a plethora of techniques that try to alleviate the memory pressure. And many of them rely on memory sharing. And the reason that we can share memory is that we reuse code. We reuse code when we run several instances of the same program. We reuse code when we use the same functions in the library. And we reuse code when we run multiple instances of the same operating system in different machines. And whenever we use code on the same physical machine, there is no point in keeping multiple copies of that code, so we share them, and we have several techniques to share that. Now, this sharing is considered safe because we share read-only. And when we share read-only, we are supposedly not being able to affect one process cannot affect another. One virtual machine cannot affect another through read-only sharing. We know this is not really true because, for example, in 2011, Suzaki and others showed that there is a small leak between virtual machines that use page duplication. But this is a small leak, and it's not considered a major threat. What I will show today is that when we say read-only, we don't really mean read-only. We mean anything but write. And in particular, we share the cache state, and we can use this cache state to create a communication channel that can leak private keys, and it can leak them much faster than was known previously. We can leak a key using a single observation of decryption or signing in a GnuPG old implementation of RSA. It is old because we reported this and they fixed the code. So the outline is I'll first give a quick background on cache architecture and describe the attack. Then I'll give a quick reminder of RSA and the square and multiply exponentiation used by the version of GnuPG that we attacked. And then I'll show how we attacked GnuPG. So as computers get faster, memory gets faster, but not at the same rate. So now memory is much slower than the processor. Reading data from memory takes about 200 computer cycles. And that's really slow. The computer has to wait for data it needs. And when it needs that same data again, it again takes a long time, and it needs to wait again. So to alleviate this, to bridge this gap, we put a cache, which is a small unit, a small memory, sits between the processor and the main memory. And being smaller and being a different technology and being closer to the core, it is much faster. And then when the processor reads the data gets stored in the cache on the way to the processor, and the next time the core needs that, it gets it faster. This also helps if we have a multi-core environment and several cores have access to the same memory, they can benefit from data being in the cache. One of the problems with caches is that at some stage they can become in inconsistent state, so the memory has new value and the cache still have the old stale value. And if the processor reads that, it gets the old data, which is not good. This is not very common. Intel architecture tries to keep the cache coherent, but it can happen in some rare situation. And we have a solution for that. There is an instruction, CL-flush, that just removes just remove part of the affected memory line. So we issue it and remove that line from the cache. And the next time that the processor needs the data, it has to read it from memory. Now, the flash reload attack exploits this behavior. We know that what it does, we have a spy process, and the spy process monitors the access of the victim to shared code in memory. And by monitoring that, the spy can create a trace of when the victim accesses this code, and by knowing what code the victim executes, we can infer what data the victim operates on. And here is how it works. We have a spy process or VM or whatever, and we have a victim running in different cores. And they have shared memory, and they have code in the shared memory. The yellow square is our code that we are interested in. And the victim accesses this code when it executes it, and the spy can access it and read it as data. So what the spy does, it flushes this from the cache, and then waits. And while it waits, the victim may access or may not access the data, may execute this code or not execute the code. When the spy finishes waiting, it reads the data back from the cache. It reads the code back. If it takes a long time, it means that the data came from memory. If, on the other hand, the spy flushes the cache, waits, and while it waits, the victim accesses the code or executes this line, then the spy read will be fast. So the spy just does a flash, reload, ladder, rinse, repeat, and so on. And this way, it creates a trace of victim access to code. And with this trace, it can know what the victim has done as a function of time. Now, how do we infer data from that? For that, how do we infer or get the key from that? For that, we need to say a quick reminder on RSA for those who, it's been many years since undergrad. RSA is a public key cryptographic scheme, and the main operation is modular exponentiation. So we compute a value b to the power of e, modulo number n, where b is the cipher or a clear text. E, in the case of decryption or signing, is a secret exponent. So it can, if we know e, we can reveal the key, and n is known. And thanks to Venkat who showed the algorithm. It's the same algorithm that Venkat showed. GnuPG version 1.4.13 uses square and multiply. It scans the bits. For each bit, it does square and reduce if the bit is clear, square reduce, multiply reduce if the bit is set. And it is well known that if we can recover this sequence of operations, then we can recover the key because we just scan it, and square reduce, multiply reduce means set bit, square reduce without multiply means clear bit. So we have a way to create traces. We have a way to infer data from the traces. We combine them together. The spy needs to achieve sharing. If it runs on the same machine as GnuPG, just up the GnuPG image. If it runs on a different virtual machine, then it up a copy of the image and waits for for page duplication to coalesce the data. We use flash reload, probe the memory about every half a microsecond, and we create a trace like this. So what we have is we have the time slots on the x-axis. We have the time that it took to read the probe on to read the code on the y-axis. And for example, in slot 0, we see that it took the spy about 280 microsecond cycles, to read the code lines that are in the multiply and reduce and the modular reduce operations, and about 80 cycles to read the line that is in the square routine. So we can infer from that that the victim was executing square at that time. And that continues for the first 3 slots, and in the 4th slot we also see reduce, so we know that in the first 4 the victim executed square, in the next it started reduce, and so forth, square. We can recover this sequence of operations. And from that sequence, we look at the first 2 operations, square reduce that is not followed by a multiply, that clear bit, and another clear bit, set, clear, set. We have recovered the sequence of operations. Now, we can, in this example, we don't see that, but sometimes we do miss operations. And the reason that we miss operations is that we're running on a system that does other things. It's not only us running there. So we have system interrupts, we have processes stopped, blocked, it happens. So how often does this happen? We have measured, we run about 1,000 signing operations on several architectures, both desktop and server class processors, both with operating system running on the bare hardware and with virtualization. And we measure the number of bits that we are missing. Now, this measurement is done with a small shell script that is very simple. The real result is that we lose a bit less bits, about 25% less if we do manual inspection of the data. But even with these results, we can see that we need, at most, we lose 30 bits that we need to recover in order to get the private key, or the secret exponent from it to get the private key. And 30 bits is something that is easy to break. Also, if we capture two signatures, then the missing bits will be in different positions, and we combine those, and with capturing two signatures, we break the key every time. So, oh, I'm a bit fast. So, other applications of this technique. We have used this technique to attack the OpenSSL implementation of ECDSA. For example, on the SecP 256K1 curve that's used in Bitcoin, we can break the private key by observing 25 signatures. So if we can get to your Bitcoin wallet and listen to 25 transactions, we have your key. Irazoki and others did the cross-VM final round attack on AES, which is, it's very nice. I didn't think it was possible to do AES with this attack. There is a guy in Canada that tries to do non-cryptographic attacks. He showed that he can trace the use of VI, just state transitions within VI. This can be used for keystroke timing. This can be used for capturing network use statistics from other virtual machines, for collocated virtual machines. And the defenses that we heard before do not protect because for the first one, the first one is only for the core share, in the case of time sharing of a execution core. The second one assumes that it takes us 6 or 10 minutes to do the attack, which, and we're much faster than that. On the other hand, we do need page memory duplication, which doesn't, it seems not to be used in public clouds. So as long as it's not used there, this is protected. Now, important lessons from this. The first lesson is that it is hard to limit the extent of sharing. Read-only is not read-only. We have seen that in the past. When we share a hyper-threading, presumably just share core, but it is not true. We share much more than just the execution. We saw earlier here that sharing USB devices is share much more than just the access to the device. And same thing we share on, when we share on Facebook, we share more than we want. So we need to remember that whenever we share anything. The other thing is that there is no excuse now. Probably it's 10 years, more than 10 years since the first side channel attacks, and we have seen them, new side channel attacks come every year. There is no excuse not to use constant time implementation of cryptographic primitives. And GnuPG fix of this was to move to a square and multiply always, which does protect against the flash reload attack, but it is still a vulnerable implementation. They then changed their implementation. They now use a sliding window, and guess what? It is vulnerable to flash reload. So, and really, there is no excuse doing that. And I don't want to pick on GnuPG. Werner is a nice guy, but the same happens with OpenSSL, and I assume it will happen with other cryptographic libraries. Now, the other and last thing is that we need to apply the principle of least privilege. The CL-flush instruction is used when we change the coherency state of the cache, and it's used when accessing some devices or some old video cards on Intel. These are system operations. So when deciding whether this should be a privilege operation or a user-level operation, we should not look at whether it seems innocuous and decide that if it is innocuous, we can put it in user space. The decision should be whether based on whether the user needs this operation. And if the user needs this operation, then we need to find a way to give it to the user safely. If the user doesn't need this operation, make it a privileged operation. That's what's done in the ARM architecture. With these lessons in mind, I'll be happy to take questions.
Okay, let's thank the speaker. And then questions?
So I'm curious, how long does it take for your attack to succeed? I didn't get from your very clearly. So you said it's less than 10 minutes, but how long will it take?
A single signature. So it is a matter of milliseconds.
Okay, that's fast.
Zhiyun Chen from UC Riverside. So I wonder if the first paper in the session, the scheduler-based defense, can actually defend against your attack.
It depends. Well, the way it is presented in the paper, and I guess that Venkat is better qualified to answer than me.
Sure. Yeah, as I told earlier, the scheduler defense doesn't really address system-level shared side channels. But as he pointed out earlier, cloud providers do not actually allow shared memory sharing in between VMs at all. And hence, that is one way these attacks will not work in cross-VM side channels. So yeah, to answer, our work doesn't really address these kind of side channels, but yeah.
Shuo Chen, Microsoft Research. So in order for your attack to be effective, you need very frequent flashing and reload, right? So I don't know why you get so many chances to flash the cache.
We get that because the attack is cross-core, so a victim runs in one core and the spy runs in another core, and the spy is not interrupted. It just flashes, waits, reloads. It's an operation that takes flashes 70 cycles. So it is, we just don't need, unlike many other attacks, we don't need to time share the core. It is a cross-core attack.
Okay, all right. So my second question is, you mentioned that at the end you still miss like 30 bits.
Yeah.
But this 30 bit, you don't even know which 30 bits are missing, right? That will also increase the uncertainty significantly.
We know the positions that we miss these bits. We know because we keep track of the time. So if we see that we have lost some time, more than 2048 cycles, we know that we have missed bits in that space.
Okay. Yeah. Thank you.
Yarom, I have one question. For KVM, I think you guys missed a lot. At least that's what the graph showed. Like 30 bits you missed for KVM machine. Is there a particular reason that happened?
There are two reasons. First, we used KVM on a Xeon processor, which we miss more in Xeon processors because of processor optimizations. And the other reason, I think, is that we put KSM to be very aggressive. Okay. And I think that it interrupts much more often than other scenarios.
Thank you.
I just want to make a quick comment about our defense paper. I just want to clarify that in order such an attack to succeed, we can reshare the keys in 2 seconds, and if we have 5 shares, so this attack simultaneously must succeed against 5 VMs let's say, or 8 VMs under 2 seconds. So you need to collocate to 5 different VMs and run this attack successfully and solve the 30 bits for 5 different ones under 2 seconds. Do you think that's possible?
Well, whether it's possible or not, I can't say. I can even add, you're absolutely right, and I can add to that, that if you have 2 VMs on the same physical machine, we'll get mixed results. The results, we'll get the noise from between the 2 VM will affect us, and we will not be able. So, if your location is such that you have multiple VMs on same physical machine, then it will be a protection against the attack. Actually, if we have 2 parallel signings on this, then we just don't get anything.
Okay, Erkay Savaş, Sabancı University. Actually, this is rather a question for the first speaker, because because what he said that his method can protect against your attack, but I don't think. Did you say? Did I get it wrong? Because I don't think it can protect it, because what you are doing, I think you are changing the scheduler, since in your attack, spy and victim process run on different cores, so it has nothing to do with the scheduler. So therefore, your attack is going to be successful in the presence of your countermeasure. Am I right?
Yes. Yeah. Sorry. I don't know if I missed it. Yeah. It's. I'm saying that it's his attack would work, and even our defense mechanisms execute. Yeah, but cloud providers do not allow page sharing by default, is what I said. Okay. Yeah, sorry about that.
All right, thank you. And let's thank the speaker one more time.
Thank you.